Okay, so this is problem 14 on post lecture 6, and you're given initial conditions right here and a rate for those conditions. You're going to use that with different conditions down here to get a new rate. Okay, and so the first thing you should see here is you're increasing the concentration of this form right here by 4 times, aren't you? And does everybody remember rate laws? No? Yes? Maybe? No? Okay. Okay. So rate laws say that rate equals a constant times the concentration of your species to its order, power, times the concentration of your other species, they're always in reactant terms, to the power of its order, okay? And so in this case, you probably have an order of 1 for these things because that's typically how that works. If you have something attacking something else, it's going to be an order 1 for each thing, and it'll be overall order 2. Okay? Meaning bimolecular, right? Two things have to come together. If this was an SN1, by the way, it would be unimolecular. Only one thing matters. And it would be that species that's unimolecular. The thing with the leaving group, right? SN2 means that you need both these things to come together. And by the way, the reason I know this is SN2 because this is a very strong nucleophile. Very strong nucleophiles will always cause it to be SN2 unless it's highly crowded. Okay? Okay, so what I'm going to do is, well, I'm going to have my constants are always equal for these things, right? Okay, so what's going to happen is that I can solve my rate laws for my constants, right? So the K is on one side, and then the other side would be my concentrations multiplied by each other divided by the rate, right? Did I get that upside down? I did, didn't I? Rate divided by the concentrations. If you write it out, you'll quickly see why I said that. So rate equals K times the concentrations, right? You divide the concentrations over. Okay. Everybody okay so far? All right. So you have one set of conditions here that you can plug in, right? That's set 1. That can be on your left side, which it is over here. Okay, so that would be your 0.05, your rate, and then you'd be dividing by your concentrations, right? Notice that's 0.5 and 1. That would simplify to 0.5, right? So you'd have 0.05 divided by 0.5 on one side. On the other would be your rate divided by your new concentrations. Well, your new rate is what you're looking for, right? So you're going to multiply over these new concentrations, which would be 0.3 and 4. Multiply those over, that would be concentration 1, concentration 2, by the way. If you're wondering what this formula right here says, that says concentration 1, concentration 2, which are these. You multiply those, multiply it by 0.05, divide it by 0.5, which is 0.5 times 1. Did anybody get lost? No? Please let me know if you're having any troubles with that. Honestly, so literally it's just rate over concentration for one set equals rate over concentration for a different set. Kind of like that V1, M1 V1 equals M2 V2. Same concept. And you solve, and you'll get a 0.12 moles per liter per second, which another way of saying that would actually be liter second down here. Curious? You should always check it against what you know. This has lower concentrations, smaller value, higher concentrations, larger value. Okay, that makes sense. If I have more fuel, it's going to burn faster, right? Okay. Anybody have any questions at all? Got confused anywhere? Anything that you or you might think somebody else might want clarified? No? Did you want to try another one? Yeah. The next one here. Let's try the B. We'll go on to the next one. Okay, so consider the reaction of 1-bromobutane with a large excess of ammonia. Draw the reactants, the mechanism, and the products. Note the initial product is the salt of an amine, which is going to be deprotonated by the excess ammonia to give the amine. I'm going to stop this and I'll start it